interests are in gravitational physics, gravitational waves, black holes, visualization of spacetimes, and computational studies of partial differential equations. He obtained his PhD from the University of Tübingen, where he was a lecturer before taking on postdoc positions at the Max Planck Institutes of Leipzig, Potsdam, Garching. He was at the University of Oxford, Pittsburgh, before joining the University of Otago. He's fellow of the Royal Society of New Zealand and the Alexander von Humboldt Foundation. And Jörg will start off the summer school with an introduction to gravitational waves. So all yours, Jörg.
Jörg, you're still muted.
I am still muted. So thank you very much for the introduction, Renate. I didn't realize that you would put my life so in public, but thank you anyway. Also, a welcome from me. And again, also from me, I'm really sorry that we have to do it in this way, because I was so looking forward to meeting everyone in person. But that's what happens when you live in a more tropical area and you have to think about cyclones and hurricanes and all these things. So before I get to the talks, let me just briefly ask everyone whether you have received the email from Chris Stevens about the labs that we are organizing this afternoon. If you did not get an email, then get in touch with us, and we'll try to sort this out during this morning. Otherwise, I'll get started with my presentations. I'm actually doing two presentations because I thought I'll spend the first hour just giving you a general overview of gravitational waves, and the second hour I will delve more into the mathematical things, the mathematical structures and descriptions of gravitational waves, still on an easy level, namely looking at linearized gravitational waves. But you will see that already this becomes a little bit more complicated. So I will give my first presentation, then we'll probably have a break of 5 to 10 minutes, and then I'll continue with the other one. So let me get started with the first one. And I'll need to share my screen.
I think you can.
Yep, I think I can. I just have to get the right things in the right order. I first have to go here. All right, can everyone see this?
Yes. Yeah.
Okay. Good, so then let me get started. I'll talk about gravitational waves, and gravitational waves obviously are waves. And so I'll first talk a little bit about waves. So we all know waves in all different kinds and shapes and forms. We know sound waves. Everyone knows sound waves. And probably everyone knows this song anyway, so let me go on. We know water waves, where you see some excitement on a surface of water, and this excitement spreads out in all directions, and it flattens out after some time. We know electromagnetic waves. They are all around us. You look at your mobile phone. This works only because of electromagnetic waves. We know light. We know radio waves that probe the universe. We know X-rays that probe the human body, and we know microwaves that give us food. So the electromagnetic waves are everywhere. We also know elastic waves. That's things that travel through some solid in a way. And and can cause all kinds of problems, like here with this bridge, or like earthquakes and other things. And apart from the elastic waves, we also know waves of this form. That's what I call a people wave. It's also called Laola. But in all these cases, what we see is that there is some motion or some movement. Something is traveling along a certain direction, and it's carrying energy and information. In this case, because the people stand up, we call this a transverse wave, because the motion of the things is transverse to the direction of propagation. In this case here, we call this a longitudinal wave. This is because the motion of the is in the direction of the propagation of the wave. And you see clearly here that there is definitely something propagating with a finite speed, and it's moving along a certain direction. So that's the characteristics of a wave. A wave is something where you disturb a medium or disturb something, and this disturbance travels along with a finite speed, with a finite propagation speed. So I guess all of you are familiar with this equation here. This is the wave equation in 3 dimensions, and in the usual non-relativistic situation where we have a quantity u that describes the phenomenon, like the the sound or the pressure in a sound wave, and we have the c here. The c is the speed of propagation. That's the finite speed with which this wave travels. And then we have on the right-hand side, we have this f. This is the thing that creates the wave. That's the source of the wave. In general, this is a very simple case with this u here. I haven't specified what it actually is in terms of its structure. The way it's written here, it looks like it's a scalar, but it can also have several components, and we will see gravitational waves do have several components. And then when they have several components, then we can have transverse waves or longitudinal waves, and combinations of those. And also one finds that different components of a wave can have different speeds. That happens, for example, in elastic waves, where we have longitudinal waves and transverse waves, and the 2 waves travel with a different speed. The common characteristic is that this disturbance that we have carries energy, and with this traveling of the wave, we can also carry or transport information. You know this from radio, where the information is encoded in the frequency or in the amplitude, or in light waves, it's also encoded in the polarizations. So there are all kinds of ways of carrying information with waves. And waves are generated. They have sources, and this is, as I said earlier, this is given by this f. Okay, so let me now come to gravitational waves. How are gravitational waves possible? The main thing that makes gravitational waves possible is the step away from the Newtonian theory of gravity to Einstein's theory. So Newtonian theory, as you probably know, is characterized by forces. You have 2 bodies, like these 2 balls here, and they attract each other by equal and opposite forces. And those forces act instantaneously at a distance. That's the principle of Newtonian gravity. And space and time are absolute entities in that theory. They are not affected by this interaction between these 2 bodies. And And so there is no relationship between these two things, the bodies, the forces, and space and time. Space and time essentially is just the stage that you use to describe this attraction here. In Einstein's theory, this is different. In Einstein's theory, each body influences the space and time around itself. This is indicated here by this hole here. The larger body makes a bigger hole in whatever this thing here symbolizes. This membrane here symbolizes. And the smaller body also makes a hole. And when one of the bodies moves, then this changes the hole, and this change in this disturbance in this medium, this travels with the speed of light and influences the other hole here, and therefore also the other body. And so via the space-time, the two bodies here interact with themselves. And that means that that space and time are no longer just a stage, but they are intimately related into this in this game, in this play that is happening on the stage. So space-time interacts with matter, and the bodies move in a deformed space-time, and that causes the interaction. And the movement of the bodies induces a disturbance in the space-time, and this disturbance travels along the space-time. So I will just mention that the Einstein equations, that's the equations that describe the deformation of space-time in terms of the bodies, the material. Einstein's equations have this form. I expect that Jörg Hennig in the next 2 days will explain much more about what these quantities here are. I will only say here that the left-hand side is the Einstein tensor. This describes the geometry. The right-hand side is the energy momentum tensor. This describes the matter. And so the equation says that a part of the matter, namely energy and momentum properties, are equal to the curvature properties of the space-time. That is part of the curvature of the space-time, and those two quantities are equal. When you write these down, and I will show you in the next hour what this equation looks like, roughly, then you find that these are 10 nonlinear second-order partial differential equations for the components of the metric, and the metric is something that describes the geometry of the space-time. So these are complicated nonlinear things, nonlinear equations, and those are complicated to handle. You have to specify what causes the deformation of the geometry, and that's the energy momentum tensor. And so you have to say what kind of matter you are using for in this description. So there are additional equations that tell you how the energy momentum tensor is composed out of the quantities that describe the matter. So if you have a fluid that describes the matter, then you have to specify the density and the pressure and the velocity with which the fluid is operating. And if you have an electromagnetic field, then here is electric and magnetic field in the energy momentum tensor. So the energy momentum tensor is a construction that is made out of the matter quantities, and so in order to have a full system, one also needs equations for the matter. So these are equations that have a particular mathematical structure. They are called tensor equations because the objects are tensors, and that means that they are independent of the coordinate systems in which one writes them down. That's something that we will explain later, but it's the crucial property of relativity. It's this validity in arbitrary coordinate systems. So there's a famous phrase by by John Archibald Wheeler that says that matter tells space how to curve, matter tells the space how to curve, and then the space tells the matter how to move. And then because the matter moves, the space also moves, and this is a circular statement here. So the first prediction of gravitational waves was in 1916 by Einstein. This here is an excerpt of the actual paper. As you can see, this is in German. It says näherungsweise Integration der Feldgleichungen der Gravitation. That's approximate integration of the field equations of gravitation. And you see down here, he talks about erste Näherung, that's first approximation, where he writes this object gamma, G here, that's the metric that we are trying to describe. This metric is given by delta, that's 0 and 1, plus a quantity gamma. And first approximation means that these gammas are taken to be small. And so it's the, as you're very well familiar, probably, it's a perturbation calculation where you have a background and a small quantity, and you're looking at the equations that govern this small quantity. So that's the calculation, or that's the paper that describes the calculation that Einstein did to obtain wave-like phenomena. And at some point, there must be a wave equation, and that's in this equation 6 in the paper here. And you see that this here is this gamma. It's a little bit changed along in the paper from the original ones. But here you have the second derivatives with respect to the coordinates. And one of the coordinates is time, and the other coordinates are x, y, z, or the spatial coordinates. And in his notation here, they all have the same sign, but that's a mathematical trick. So what this equation here really is a wave equation for this gamma mu nu prime, and they are sourced by this term here, which is the energy momentum tensor. Okay, so some of the properties, so this paper says that there is the small perturbations in the metric, they satisfy a wave equation, and you can read off then from this wave equation what is the speed. Speed turns out to be the speed of light. One also finds that the waves are transverse, so they perturbation acts perpendicular to the direction of the traveling of the wave. And it also has two different states, like an electromagnetic wave that has two polarization states in two different or two perpendicular direction. A gravitational wave also has two polarization states in which it stretches the space in anisotropic ways, but in two different ways. And when you look at this here, this is what a gravitational wave does to a ring of particles, if you want. It stretches it out in one direction and compresses it in another direction. And those two directions are perpendicular to each other. But from one state to another state, they are rotated by 45 degrees. And so we have these two independent polarization states that make up an entire gravitational wave. So those things that I'm claiming here, I will discuss in more detail in the next hour, how these things come about. A useful way of looking at the strength of a wave is to look at the strain, and this is the relative change of the length in the stretching and compression of the space or space-time. This is given by a quantity which is called delta L over L, and you see here that the delta L is the change in the length and L is the actual length. This is a dimensionless quantity. All right, so this here is a representation of a gravitational wave in one particular polarization state. It looks weird. but it travels along a certain direction, and then perpendicular to that direction, it stretches out in and compresses into directions that are perpendicular to each other. And so this is, gives you an idea of what this thing here looks like. But apart from that, there is not much more information in this. So let's look at the emitted power that one can compute for the wave. One can derive a formula for the strength of a gravitational wave that is emitted by a particular source, and it very much depends on the dimensions of that source, and the mass, the dimensions, and the motion of that source. And you can see here the power that is generated is when you take a rotating bar. So that's just a, I'm trying to find my cursor here. I don't see it. Well, so this is just a cylinder that you're rotating around, a cylinder of a mass m, of a length L, and you rotate it around with a frequency omega. Then the emitted power you find is this formula, where P is omega to the power 6, mass squared, and length to the power 4. One can make this a little bit more quantitatively with units, and then you find that the power that is emitted, measured in watts, is equal to 10 to the minus 52 times the frequency measured in hertz, the mass to the power 6, the mass in kilograms to the power 2, and the length in meters to the power 4. When you then plug in some numbers of objects, then you are very easily disappointed. So if I take a pen like this and I rotate this around, so the rotating pen here, if I do this, then I have 10 to the minus 64 watts. That's not much. And that's why Einstein in his paper said that in all conceivable situations, this is vanishingly small. So this is disappointingly small. And so the implication was that you will not be able to see this. Now, we have much more powerful systems than a rotating pen. And the most powerful systems that we have in the universe are probably those binary systems that consist of two black holes, where the black holes are rotating one around the other. And while they are doing this, lose energy in the form of gravitational waves. And so one can think about how much power is emitted by those. So here's the rotating pen again, 10 to the minus 64. If you look at the system that consists of the Earth and the Sun, then you find that it's just a light bulb, a stronger light bulb, an old one, not a modern one. Jupiter's sun is a little bit more, that's a heat pump. And the double pulsar, that's an object that is has two neutron stars rotating around each other. That's two objects with about a couple of solar masses in a distance of 10 kilometers. And I think this is wrong. This is 10 to the 4 hertz. And then you get a sizable quantity. Then you get 10 to the 45 watts. So the extreme systems do emit gravitational waves in a reasonable power. So what do we expect when we look at the system of two compact bodies? We expect that they lose energy because the energy goes away in terms of in the form of gravitational waves. Because of the loss of energy, they come closer together, and because the angular momentum is conserved, this means that the frequency goes up. So they rotate faster, which means that the gravitational wave frequency also goes up. And and then in the end, there will be a violent collapse to a single object, which is a single black hole if we start out with two black holes, and then the system settles down. So what you see here is the expected waveform, and that one can compute numerically, that one can compute from this process, and it should sound somewhat like this. And that's all the familiar things nowadays, I guess, that that you have seen and heard before. So the gravitational waves have been, the existence of gravitational waves has been predicted, and it has been confirmed, at least indirectly, already a couple of decades ago, where one has observed the period of a binary pulsar, and one observed that the period went down because of this reduction, or the close coming close of the object. The period goes down, the spinning up happens, and it happens in a way that is compatible with general relativity. And so this is one of the famous plots that was in the years before the discovery of the gravitational waves with LIGO. So that was the main plot to show that gravitational waves actually do exist. Nowadays, we know that they exist, and we know this because these detectors have all been built, and at the moment, I think we still have, I think we have more now than 4 detectors. Because the Kagra, I think, is operating. I'm not sure. Someone must correct me there.
Kagra is operating, Jörg.
Kagra is operating.
Yes.
Yeah. And so we have now how many? 5 operating detectors, and so these are the detectors that I'm aware of. The first one was built in Hanover. It's called GEO 600. Then we have the LIGO detectors. We have Virgo detector in Pisa, Kagra in Japan, and there is talk about the LIGO in India. It's a huge international collaboration, which is funded by all kinds of science funding agencies like the National Science Foundation, the Max Planck Society, the UK Research Council, and Australia's Research Council, and many more. So the expected strain, what I talked about earlier, that's the ratio of changed length to the actual length, is it's around 10 to the minus 22. So this is this ratio corresponds to the diameter of an atom compared to the distance between the Sun and Saturn. So this is quite a small ratio, and you need very sensitive detectors for this. And so that's why one has introduced these laser interferometers on Earth and in space. So here is a small video that I think how am I doing in time?
30 minutes so far.
Sorry?
30 minutes to go for the first hour.
Okay, so then I'm good in time. So that's a small video that explains the operation of the of a laser interferometer. So you have a laser. It sends out a laser beam that is split, and then the 2 parts travel to a mirror and come back to the beam splitter, are reunited, and then come to the detector here. And as you can see, when the mirrors move, like here, this changes the signal that one sees here. It changes because of the interference, it changes the light intensity here. And so by measuring the change in the intensity here, you can say something about how the mirror have moved. And that's the principle on which the laser interferometric detectors operate. And you see this shape here. The fact that you have these lengths here and here perpendicular to each other. You see this in the design of the detectors. So this here is a picture of GO600, and you see very clearly that if I had a pointer, then that would be nice, but I don't. And you see very clearly that you have these long arms, and in the left lower corner there is all the machinery. That's where the laser is and where the laser, the diode. Yeah, thank you. How do you do that? So here is that's the center. This is where the beam splitter is, and then you have the two vertical arms. These are the two LIGO detectors with their long arms. These are arms that are 4 kilometers long. GO600 has arms that are 600 meters long. That's why you have this number 600 in them. Again, you see this L-shaped form, and then we have Virgo in Pisa again with the L-shaped form, and then we have something that is planned, which is not L-shaped, and this is LISA. It changes its shape every I don't know, 10 years or so. So this is a picture that was once thought of being the design of LISA, but this is just an artist's impression. So LISA will be a space antenna that consists of 3 satellites that are following the Earth around the sun, and a lot of work is currently going into the design of that project and the science that can be done with that laser antenna, space antenna. Okay, so now I'll show you a computer simulation of the first detection of gravitational waves. So that's when the 2 black holes are merging together. What you see is a surface that describes a mathematical quantity called the lapse function. And the lapse function tells you something about the marching of time in that entire system. And and the deformation of that surface says that the time is more or less delayed depending on the properties of that surface. There are arrows here that have to do with, that are called the shift vector. The shift vector tells you how the space is stretched mainly in which direction the space is stretched. And so if I run this, when I run this movie here, then you'll see that the 2 bodies that are here given above, they circle around each other, and while they are circling, this surface here also changes its shape. So this is in a sense, well, I cannot stop it. Okay. So this is in a sense that surface that I talked about when I explained the differences between Newton and Einstein. You can think of it as being the surface of the lapse function. And so we have these bodies rotating around each other. They are coming closer, and that means that the time is slowed down because the gravitational field is getting bigger because the bodies are coming closer. The bodies are moving faster, so they are rotating faster. And when they are at a particular distance, then something happens with the shape of these bodies here. As you can see, suddenly there is a surface that encompasses both of the bodies, and that is the horizon that has the common horizon that has formed, so that the two black holes have merged into one black hole, and this one black hole then settles down. And this here is another simulation where one looks at the same system, the two bodies, against the backdrop of the Milky Way, and because the gravitational field or the deformation of the space-time influences how light travels, this also influences how we see things. And in this case, what is looked at here is what the Milky Way would look like if in the foreground there would be this merger of black holes, and I'll just run that movie. Again, you see how the black holes rotate around each other, and how the we see this as the stars moving around, but it really is just the light rays that are reflect, or that are changed in their path, deflected, and that's why we see this movement. You see, once we have a single black hole, then it very quickly settles down. I'll show it again. I like this movie because it looks somewhat realistic, whereas the other one with showing the lapse function is mathematically nice, but it doesn't show you anything what you might see. Okay, so that's the simulations of the black holes. You will hear a little bit about numerical relativity, which is the way that these, at least as well, both of the movies actually have been produced. So Chris will talk a little bit about numerical things, and you will have lectures on all the aspects that I have touched on. The sources, we'll have lectures on the sources, we'll have lectures on the detectors that are planned and operating, and we also have lectures on how you actually extract signals from this change in the intensity in the laser detectors. So I think with this, I'll stop my first talk, and I'll leave the last sentence to Einstein, who I think was right in the end about the existence of gravitational waves. So I'll stop here, and I'll continue with the second talk in maybe at 10 or so. And in the meantime, I'm open for questions, and let's see what people have, what questions people have. I cannot actually open the chat. Well, let me.
Thank you very much, Jörg. Can you see the chat?
Now I can. I had to go away from full screen.
Okay.
Ah, there is an annotate button.
Yeah, as Jörg said, Jörg's happy to answer any questions regarding his talk. So please.
So if there are any questions, ask me. You can also ask me, during the break or so. I'll stick around, and yeah, whatever suits. Okay. No questions? So, Renate, what do you think? Should we wait until 10 or get started at 5 to 10 or so?
Yeah, 5 to 10, I think would be good. That gives everybody a few minutes to maybe grab a cup of tea or a coffee and stretch
Yep,
the legs.
that's exactly what I intend to do.